Thanks a lot for the invitation. I'm very happy to be here and speak about condensation in random trees. It will be essentially a blackboard lecture. Maybe there will be some pictures, films, animation, science fiction at the end, but we'll see. So I'll give you the menu. Lecture 1, we will introduce the objects we will work with, which will be Bienaymé, Galton, Watson trees. BGW in short, and their codings. We will code them by random walks. So this will be today. Tomorrow, lecture 2. We will study random walks which appear in this coding, and we will establish a one big jump principle for these random walks. And lecture 3, which is 1 plus 2, we'll combine this and this to get information on random trees, applications to random trees. So since the exercise session is this evening after the first lecture, I won't spend too much time on history, motivations, and so on, to really define some objects and give us some material to work with this evening. And maybe I'll give some more overview and so on at the end of lecture 3. But some history. The Bienaymé, Galton, Watson, this is in the 19th century. Bienaymé and Galton, Watson studied the Bienaymé, Galton, Watson processes. They were interested in the question whether noble family names would disappear or not. So they proposed some models and studied these questions. And then we go to Aldous in the 90s, who really wanted to understand the global structure of random trees, not just processes, how the number of people evolve in a certain population as time grows, but really the whole structure, the whole genealogical tree structure. And this is connected to the Brownian CRT. And the condensation phenomenon was noticed by Jonsson and Stefánsson in 2011. And this will be the phenomenon we will be interested in. And the random walks part, estimates on random walks goes back to Nagayev, I think in the 70s, works by Rondoni, Denisov, Dicker, Schneer. This is 2007, I think. And the one big jump principle we will study is due to Armendariz and Loulakis in 2011. Okay, very quick history. And there are some lecture notes available on my webpage. So if you want details on everything, you can have a look. Dot. Okay. And one of the reasons I wanted to talk about this subject is that we can arrive to a nice phenomenon nice results, condensation random trees, in a rather self-contained way. So the results I think are pretty nice because okay, it's I think a nice geometrical result on random trees, but you use different tools, especially random walks, and the tools and ideas we will use I think can be useful in other contexts. Okay, so today I will introduce Bienaymé, Galton, Watson trees. Their codings by random walks. I will go rather fast. I won't give much proofs. So if you're interested, everything is here. But the goal here is to go rather fast, but still to give the intuition. And if at any point something is unclear, please ask. So lecture 1. Bienaymé, Galton, Watson trees and random walks. So first, trees. What are trees? Trees are everywhere. So for me, a tree is always a plain rooted tree. So this is a tree. This is another tree. And for me, as trees, plain rooted trees, they are not the same. Because here, the root has 2 children. The first child here has 0 children, whereas here, the first child has 2 children. So as plain rooted trees, they are not the same. Trees are plain and rooted. We can give a precise definition by coding the vertices of the trees, by saying that the root is the empty set. The first child of the root is 1, the second child is 2, the first child of 2 is 2, 1, the second child of 2 is 2, 2. Here the root is empty set. The first child of the root is 1, the second child is 2, here is 1, 1, here is 1, 2. So you can code this tree by the set, empty set 1, 2, 2, 1, 2, 2. And indeed, this set is not the same as this set. So it's possible to using this formalism of subsets, of sequences, of integers, to give a formal definition of what a plain rooted tree is. But I won't go into details. You can have a look in the lecture notes if you want, but I hope that at least the intuitive definition is okay. Okay, and here I will need a definition. Ku is the number of children of U. Okay, now to study plain rooted trees, a very useful thing is a coding by a path, which is called the Lukasiewicz path. So definition of the Lukasiewicz path. Let T be a tree with n vertices, which I order u0 smaller than u1 up to un minus 1, using a certain order, which is the lexicographical order, using the lexicographical order. So what is the lexicographical order? It's the lexicographical order on labels. So here you have vertex 0. Here you have vertex, let's write it u0. Here you have vertex u1. Here is vertex u2. Here is vertex u3. Here is vertex u4. Here you have vertex u0, u1, u2, u3, u4. Another way to define the lexicographical order is to do the contour of the tree, and you mark vertices the first time you see them. So here u0, you go around the tree like that. u0, u1, u2, u3, u4. Okay? There are different orders you can take. You can take, this is roughly speaking the depth first search of the tree, but there's also the breadth first search and so on, but we will only work with the depth first search. Okay? And then define the path W of t, which is W0 of t, W1 of t, and so on, up to Wn of t, by W0 of t is 0. You start at 0, and then you do jumps. And the jumps you make are connected to the number of children. Wi plus 1 of t minus Wi of t is the number of children of ui minus 1. So I'll give an example just afterwards. So in other words, to define the Lukasiewicz path, you look at the vertices in lexicographical order and you make jumps, and the jumps are equal to the number of children minus 1. So for example, okay, so let's take this tree. I order it in lexicographical order, U0, U1, U2. So I follow the contour of the tree, U3, U4, and I mark a vertex with a new label the first time I see it. Okay. So this is t, this is W of t. It starts at 0, and then at 0, you look at the number of children of U0, and you make a jump equal to the number of children minus 1. So here you see 3 children, so you make a jump of size 2. Then you look U1, you make a jump equal to the number of children minus 1. Here you have 0 children, so you make a jump of size minus 1. U2 has 2 children, so you make a jump of size 1. U3 has 1 child, so you make a jump of size 0. U4, 0 children. U5, 0 children. And U6, 0 children. So here you have a path which has certain properties. It is integer valued because children are integers. When it makes a negative jump, it's of size at most 1. And here something interesting happens. You touch minus 1 for the first time at time 7. And this is not a coincidence. Actually, you can check that the Lukasiewicz path is a bijection between trees and path in the following sense. The map between the set of all trees with n vertices, which goes to a certain set which I will call S bar n, which to a tree T associates not the path but the jumps, so KUI minus 1 for I between 0 and n minus 1. So here, instead of looking at the path, I only look at the jumps. This is a bijection where S bar n is the set of all jumps which give you a path like that. Formally, you make n jumps which are integer valued in the set minus 1, 0, 1, and so on, such that you finish at time n in minus 1, but you do not touch minus 1 before time n. I will not give a formal proof, but again you can see the proof in the lecture notes. But the idea is to do an induction. Okay, roughly speaking, if I give you the path, how can you reconstruct the tree? Well, you do it inductively by first looking at constructing what happens around the root. If you make a jump of size 2, it means that the root has 3 children. And then inductively, you look here at the first time you will hit this level, which is here. The first time you will hit this level. The first time you will hit this level. This part will give you the first subtree grafted on the root. This part gives you the second subtree grafted on the root. And this part gives you the third subtree grafted on the root. So it's an inductive procedure. Okay? So again, if something is unclear or clear, please ask. So for the moment, everything is deterministic. And now we will do probability by choosing the trees at random in a certain way, and then ask how the associated random path behaves. So Bienaymé Galton-Watson trees. To define a Bienaymé Galton-Watson tree, we need an offspring distribution. Take mu of I to be a probability on the non-negative integers, which we view as the offspring distribution. We view mu of I as having the probability. We view mu of I as the probability of having I children. So a Bienaymé Galton-Watson tree is the simplest genealogical tree you can imagine. You start from one ancestor who has a random number of children. The law of the number of children is distributed according to mu. And then recursively, the children of the ancestor have a random number of children, all distributed according to mu. And everything is independent, and everything has the same distribution. Really the simplest genealogical model you can imagine. Okay, so formally, okay, then define for a finite tree T, P mu of T to be the product over all the vertices of T, mu of the number of children of U. So this formal definition comes from the intuition that the number of children having Ku children appears with probability mu of Ku. The theorem, assume mu of 0 plus mu of 1 less than 1. Here I mention this condition, and we will always assume that this condition holds in the sequel. It's just to avoid the degenerate cases. If this is equal to 1, you can have only 0 and 1 child, so it's not that interesting. So this is to avoid trivial cases. Then if the average number of children is at most 1, then P mu is a probability on the set of all trees, of all finite trees. So this is just essentially stating the fact that if you take this genealogical model, if in average do not have more than one child, you will get almost surely extinct. Your tree will always be finite. And conversely, it is possible to show that if in average you have more than one child, then with positive probability, your tree can be infinite. And in this case, this P mu is not supported on the set of finite trees. But we will work with finite trees, and this is possible under this condition. And the proof is essentially the study of a fixed point equation. And again, the proof is in the lecture notes if you want to see it. Are there any questions on this? Okay, so let's continue. We have our probability P mu on trees, and now if T is a random tree, by random tree I mean a random variable taking values in the space of finite trees is a random tree with distribution p mu. If its law is p mu, we say that T is a Bienaymé Galton-Watson tree with offspring distribution mu. Okay, so now the question is for a Bienaymé Galton-Watson tree, how does its Lukasiewicz path behave? Since jumps of the Lukasiewicz path are connected to number of children, and the number of children are IID with offspring distribution mu, it's natural to expect that there's a random walk behind it. But since there's this positivity condition, meaning that we touch -1 only after we explore the whole tree, there will be some positivity conditions on the associated random walks. Okay, so let's see what this gives. So what is the associated random walk? The probability of having I children is mu of I. So the probability of making a jump of size k is the probability of having k plus 1 children, meaning mu of k plus 1. So naturally, we introduce the random walk Wi such that W0 equals 0, and the probability of making a jump of size k is mu of k plus 1 for k at least 1. So this is our main character, and as in Game of Thrones we will maybe kill it. So we set zeta, the time when we kill the random walk, which is the first time the random walk touches -1. So again, it's rather natural because here the Lukasiewicz path touches -1 and it stops. But for the moment, for such a random walk, maybe for the moment we do not know if this is finite or infinite. So here for the moment, the first hitting time of -1 is either finite or infinite. For the moment, we don't know. So this is a zeta. Okay. So now the following result identifies the Lukasiewicz path of a Bienaymé Galton-Watson tree as the random walk stopped at time zeta. So proposition, let T be a Bienaymé Galton-Watson tree. Then the Lukasiewicz path stopped. So here, when we finished exploring the tree, this is the size of the tree, its number of vertices. So I'll write it like that. Has the same distribution as the random walk stopped at time zeta. So these are vectors of random length. Okay. In particular, so here I use W. So it's a slight conflict of notation. Here, the W's are not the same. If I write W of T, it's the Lukasiewicz path. If I write just W, it's the random walk. Okay. So in particular, the total size of the tree has the same law as zeta. And since the Bienaymé Galton-Watson tree is almost surely finite, we get for free, for this associated random walk, that actually zeta is finite with probability 1. So here it's a nice way, starting from trees, to obtain information on random walks. We know that the tree is almost surely finite, And by this correspondence, we get for free that the first hitting time of -1 by the random walk is almost surely finite. And also, if Tn is a Bienaymé Galton-Watson tree with Osmond distribution mu conditioned on having n vertices, I always assume that the conditioning is non-degenerate. Is a Bienaymé condition tree with n vertices. Then what? Then the Lukasiewicz path, which stops at time n because we have n vertices, has the same law as our random walk under the conditioning that it touches -1 for the first time at time n. Again, I don't give the formal proof, but I hope that intuitively it's clear almost by construction. But again, if you want to write the proof, it's a bit painful, but okay, so now we see that our goal is to understand the behavior of large Bienaymé Galton-Watson trees, and we have a coding by random walks. So from now on until lecture 3, we will focus on these random walks and try to understand what do they look like. What does this conditioning on having a late return to -1 for the first time imposes on the random walk? And this conditioning zeta equal n, hitting -1 for the first time at time n, it imposes a positivity constraint on the random walk on what happens before time n. So it's a non-local conditioning, which is rather delicate to study. And to study it, the main idea is to do cyclic shifts on the increments of the random walks to try to get rid of the positivity condition. And this goes through the cyclic lemma, which is a deterministic result, which will then apply in the context of random trees and random walks. So the cyclic lemma will essentially tell us that instead of working under the conditioning we touch -1 for the first time at time n, we can work with the conditioning we touch -1 at time n. So we can remove the positivity constraint before. Okay, so I need some definitions to state the cyclic lemma. Set Sn to be the set of all increments of paths such that we touch -1 at time n. Okay. And recall that we have defined S bar n to be the set of paths which touch -1 at time n, but such that before we have not yet touched -1. Okay. And now we will do cyclic shifts on elements of Sn. So what do I mean by that? So by cyclic shifts, I mean cyclic permutations indexed by z over nz. So we identify z over nz integers modulo n with their unique representative between 0 and n minus 1. And for a vector x, I will put a line under it to say that I'm working with vectors. I z over nz. We define x parenthesis I to be the shifted increments x1 plus I, x2 plus I, xn plus I, with addition modulo n. So let's see what this gives on an example. If here I represent the walk associated with the x's. I see the x's as the jumps. Here is the associated walk. So here x is, I first make a jump of size 1, then -1, then -1, then 1, then -1, then 2, then -1, then -1. Okay? So now what is, for example, x of 5? So this means that I start at 1, 2, 3, 4, 5. I start here. And I read the jumps starting from here. So I will have 2, -1, -1. 1, -1, -1. 1, -1. And if I represent it, 2, -1, -1, 1, -1, -1, 1, -1. Okay. And now the cyclic lemma tells us for how many i's I fall into S bar n. I have no positivity constraint. I make the cyclic shifts for how many times will I get at the end this positivity constraint. For every x in Sn, I set Ix to be the set of all i's such that when you do the cyclic shift, you are in S bar n, meaning that you touch -1 for the first time at time n. Then the cardinal, the number of times you do this, is always equal to 1. The I depends on x, but the number of times you get the positivity constraint does not depend on x. It always is equal to 1. And the element of Ix is the first time the associated walk touches its infimum. So what does this mean? It means that if you look here, your walk, its infimum is equal to -1. You look at the first time it hits -1, it's here, so it's time 1, 2, 3. So let's see, what is x3? You put your origin here and you read the jump starting from here. So you read 1, -1, 2, -1, -1, 1, -1, -1. So let's see what we get here. 1, -1, 2, -1, -1, 1, -1, -1. And indeed, for this cyclic shift, you touch -1 for the first time at the last time. And what the result tells you is that there is no alternative, no other choice. So the proof is essentially just combinatorial manipulations. You can prove it by many ways, by induction, but you can try to figure it out yourself or look for the proof in the lecture notes. Are there questions on this? So now, applications of the of the cyclic lemma. So now the applications in the context of random walks is to show that certain properties of the random walks conditioned on zeta equal n are, can be calculated by using just the conditioning Wn is equal to -1. So let's see this, and first we will do it for functionals of the random walk which are invariant under cyclic shifts. So what do I mean by this? So let f from Zn to R be a function invariant under cyclic shifts, meaning that for every x in Zn, for every I in Z over Nz, when you look at the function at x, it is the same as the function after cyclic permutation of the jumps. So can you give me examples of functions invariant under cyclic shifts? Now we have to wake up.
The sum.
The sum, yeah. The product. Okay. So any function of the symmetric functions in the xi's, indeed. Okay, another one, maybe less constant. Okay. Yeah, that's. Yeah. Yeah. Then in the theorem, we should check that for a constant, the result works. Yeah.
Sum of xi minus xi plus 1 to the power of 4 or something like that.
You mean the sums to some power?
But
Or
of the differences xi minus xi plus 1, for example.
okay. So you mean you look at the sum from I equal 1 to n, xi plus 1 minus xi to some power p, with xn plus 1 equal to x1. Yeah, okay. So indeed, okay, so these functionals are, so in various applications, indeed, when you work with random walks, you get sometimes you have to estimate stuff like that. And maybe one which is maybe a bit less, not of this form, but which will be very useful for us sometimes, it's the maximum. The maximal jump is invariant under cyclic shifts, the minimum as well. But for example, the first jump, x1, is not invariant under cyclic shifts. Okay. So now, proposition. Let f be invariant under cyclic shifts. Do you manage to read here? It's okay. It's not too okay. Under cyclic shifts. Okay, 1. Okay, write Wn. We call the Wn is our main character. It's the random walk. Okay, 1. We look at the expectation of the jumps of the random walk. Indicator zeta equal n. So we look, we restrict ourselves to the event when we touch -1 for the first time at time n. Then this is the same as if we remove the positivity constraint. We replace zeta equal n by just WN equal -1, but there's always a price to pay. So we get 1 over n. 2, probability that z equal to n. The probability that a random walk touches -1 for the first time at time n is equal to 1 minus n probability that Wn is equal to -1. Okay, now we will prove this. Because I think the proof is quite nice. It's not very difficult, but it's a nice proof. Well, yes.
Maybe it's stupid, but is there something similar with instead of like 1? I mean, can we generalize to k, and for it's greater than 1? Like, can we substitute k where there is the 1, let's say?
Yes, yes, yes. I wanted to, since here I will only work with trees, you get a tree, it's one tree. But if you work with forests of trees, you take, for example, k trees, and you look at the Lukasiewicz path. So you do the Lukasiewicz path of the first tree, then the second tree, and so on. Then you will touch -k for the first time at time n. And so there, this is in the setting of trees. In the setting of forests, you can replace zeta by zeta k when you touch -k, yes, for the first time at time n. And here you will get k, and you will get k. So this is, yeah, there's a remark in the lecture notes on this, so you can have a look if you want. But here I wanted to avoid introducing too much notation, and this will suffice for our purposes, but indeed, there's a natural extension. Yeah, thanks. And the extension of the cyclic lemma is that if you want to touch -k for the first time at time n, and you do cyclic shifts, then there will be always k possible ways of doing it. In the cyclic lemma, you have to replace equal 1 by equal k. Other questions? Okay, so proof. The fact that the main thing is to prove 1, because once we have 1, we take for f our favorite function invariant by cyclic shifts, which is a constant. And by taking f equal to 1, we get 2 from 1. Okay, so let's prove 1. Okay, so some notation to simplify life. Set x like that to be the vector of increments of the random walk. Okay, and now notice that the event zeta is equal to n, we touch -1 for the first time at time n, is exactly the event. This increments are in S bar n. And the event we touch -1 at time n is precisely the event. The increments are in Sn. Okay, and just a side remark. So back to here in the cyclic lemma. So you can ask yourselves what happens if the random walk is not downwards free anymore. So in the cyclic lemma, in Sn, S bar n, the increments have minimum value -1. So you can ask what happens if I take random walks on the integers. Is the cyclic lemma still true? Is this still true? So you can ask yourselves that. Okay. Okay, back to the proof. So the quantity we're interested in is this one. And we have to manipulate it to get this. And the idea is to use the invariance by cyclic shifts and force cyclic shifts to appear. And the probabilistic reason is that if you have increments of a random walk and you do a cyclic shift, this does not change the law. It's if you have n increments of the random walk, you do a cyclic shift. Of course, the jumps change, but in law, you still get the same. So here, I will. Okay, I will. So notice that this and that for every I in Z over NZ, if I cyclically permute the jumps, I have the same law. The law does not change. So here, by this third remark, I do this. I replace all the xn's by the cyclic shifts. Okay, because all these expectations are equal to the same one, which is this one. Okay, so now I use the fact that f is invariant under cyclic shifts. And now the advantage of this is that f of xn does not depend on I anymore. So now you can use linearity of expectation and put the sum inside. So you get 1 over n, sum expectation of f of xn, sum from I equal 1 to n, x and I indicator x and I is in S bar n. And here I add indicator xn is n in Sn. Here, to add this indicator, I just use the fact that if we are in S bar n, then we are in Sn. So I can add for free this indicator. And then the key thing is to notice that the sum, but yes, is equal to indicator xn is equal to Sn by the cyclic lemma. When the sum of the jumps is equal to -1, you look at how many times after a cyclic shift you get your positivity condition, and there's only one time. You do not know where it is, but there's only one. And so finally we continue and get that this is equal to 1 over n expectation of f of xn, indicator xn is in Sn, and this is precisely what we wanted to prove. So the proof is rather short, but so it's there's two ingredients. One is a deterministic ingredient, which is the cyclic lemma, and one of more probabilistic flavor, which just tells you that cyclic shifts of IID random variables does not change the law. Are there questions on this? Okay, so if not, now let's continue and try to get a result without some condition on cyclic shifts. So here, what this result says is that if you are interested in some functionals which are invariant under cyclic shifts, you can just replace the conditioning zeta equal n by a conditioning wn equal -1. And if you want to apply this for random trees, remember that the xi's correspond to, roughly speaking, number of children. So you can use this result to study random trees. For example, if you are interested in the maximum number of children, the sum of the number of children, the product of the number of children, and so on, you can use this result to study random trees. But the question is, okay, but can you use such results to really understand the global picture of the tree without just looking at functionals, which are invariant under cyclic shifts? In other words, can you obtain a simple description of the law of the random walk conditionally given zeta equal n from the one conditionally giving wn equal -1? And we will do this using the Vervat transformation, which I will now describe. Definition of the Vervat transform. So take x to be in Sn. So this codes, these are increments that code a walk which touches -1 at time n. And then we set the Vervat transform of x is x cyclically shifted at the unique element of ix. Here there's a slight abuse of notation. I identify a set with one element with the element inside. So for example, if I take this, what does the Vervat transformation do? It does a cyclic shift at the unique element, which gives me at the end the positivity condition. And we saw that this unique element is the first time the associated walk reaches its infimum. So you look at the walk associated with the increments. You look at the first time it reaches its infimum. You put your new axis here. And you read the jump starting from here. So here you will read 1 minus 1, 1 minus 1 minus 1. So the Vervat transform is 1 minus 1, 1 minus 1. Okay. Is the definition clear? Okay. So now a theorem. Okay, so let's look at the Vervat transform of x1, xn under the conditional probability Wn is equal to -1. You condition your random walk on being at time n in -1, and then you do the Vervat transformation.
So just to be sure, when
Yes.
you say you condition to be in -1 at time n, it could be in -1 before.
Exactly.
As well.
Exactly. It could be.
Yeah.
And if it does, you do the Vervat transformation. But if it is not at -1 before time n, this Vervat transformation does nothing. Does not.
Be the same
Yes.
thing.
Yeah. Yeah. So this has the same law as x1, x2, xn under the conditioning zeta equal n. So this tells you that if someone takes a random walk condition on having Wn equal -1, then does the Vervat transformation. And on the other side, someone simulates a random walk condition on zeta equal n, then you cannot tell the difference. They have the same law. Okay. 2, condition under the conditional probability Wn equal -1. The Vervat transform and the location where you did the Vervat transform are independent. And I of x1, xn is uniform on 0, 1, and -1. Okay, so again, here, this result tells you that if you want to simulate something under the conditional probability zeta equal to n, so if you want, for example, to generate the Lukasiewicz path of a random tree condition having n vertices, what you can do is first simulate a random walk conditionally giving Wn equal -1, and then do the Vervat transformation. So in particular, for simulation purposes, it's rather convenient because if, for example, if you want to do rejection, zeta equal n, you have a lot of more constraints than Wn equal -1. Okay, so this is the first part. And the second part tells you, okay, simulate a bridge, conditionally given Wn equal -1, do the Vervat transformation, and look at the end. Here you get v of x, and what was I? Here I was 1, 2, 3. And the second item tells you that at the end, this path with positivity constraint is independent of the index where you did originally your transformation. And a side remark is that if you have a bridge like that, the location of the first time it reaches its infimum is uniform on 0, 1 to n-1. Are there any questions on the result before turning to the proof? So the proof uses a bit the same ideas as before of 1. So here, okay, let's see how this goes. Take so let's, as before, set xn to be the increments of the random walk. Take x in S bar n. So here the bar is important. And let's consider probability So let's see what this gives. So I look, again, I do this trick with cyclic shifts. Okay. To check, is it like that? Let's see. Okay. 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 Now I replace. I want to use linearity of expectation. So I transform the probability into an expectation. Okay, and now I write this as expectation of 1 over n, expectation, sum from k equal 1 to n, indicator x and k equal to x, indicator wn is equal to minus 1. Okay, so this is the main idea. So now you look at what is here. Here you have a bridge, so the sum of the increments is equal to minus 1. And you look, how many times does a cyclic shift give x? Well, x, I took it in S bar, so I know that this cyclic shift will be in S bar n only once. For which index k? Well, for the index I of x1, x2, xn. And in this case, the unique element k, which gives this thing in S bar n, this will be the Vervat transform of xn. So this will be 1 over n, expectation, indicator, Vervat transform of xn equal to x, indicator wn is equal to minus 1. And we get 1 over n probability that the Vervat transform is equal to x, wn is equal to minus 1.
Sorry, can you repeat just the last?
Yes. This one or this one?
That one.
This one. What I'm saying is that okay, can I write it or just explain it? When wn is equal to minus 1, there is only one k in z over nz such that x and k is in S bar n, and this index is I of where did I put my orange chalk? So is it, does this make more sense? So in this sum, there's only one indicator which is maybe not 0. The only one which is maybe not 0 is the one for which x and k is in S bar n. And for this one, this x and k is equal to xn shifted here. And this element is then the Vervat transform of xn. And when there is really this element non-zero, well, it's when it's equal to x. Okay. Okay, now to conclude, the last thing is just to notice that this is the same, this probability is the same as the probability that xn is equal to x and zeta is equal to n. Actually, these two events are the same because x bar is in S, x, the vector x is in S bar n. Okay. And to conclude, then divide by probability that zq is equal to n is 1 over n, probability that wn is equal to minus 1. Okay, maybe to and moreover, xn is equal to the Vervat transform by definition. Okay. Are there other questions on this? Okay, so if not, let's prove the second part. Where can I erase? Okay, so let's see for the second part. Let's look at the probability that the Vervat transform is equal to x and the I of xn is equal to k on the event wn equal minus 1. Okay, so what is this? This is the probability that the increments of the random walk shifted at the first time it reaches its infimum is equal to x, and I of x n is equal to k, wn is equal to minus 1. And here I take x to be again in S bar n. Okay, so now on this event, I know where the location of the first time I hit the infimum is. It's k. It means that to do the Vervat transform, I have cyclically shifted at k. So I just replace this I of xn by k. So this is the probability that x and k is equal to x I of xn is equal to k, wn is equal to minus 1. And now the trick is to simply remove this event. Once you have replaced this I of xn by k, you can forget about this one. So this is the trick in this proof. Why? Well, again, here I took x in S bar. So if you have shifted at k and you get an element in S bar, since you know there is only a unique way to do cyclic shifts to get a positivity constraint, if shifting at k you get the positivity constraint, then for sure you know that the place where xn reaches its first infimum was at time k. So these two events are the same. This is the trick in this proof. And now, here, by using the fact that the increments are invariant in law under cyclic shifts, here I simply write that this is probability that xn is equal to x. Okay. Okay, so now what do we get? So here you say, okay, I want to condition on Wn equal -1 here and here, but here there's a slight subtlety, is that x was taken in S bar. So if you sum here over all x in S bar, you do not get this event, because here x is in S bar. If you sum all these events, you will get exactly the probability that zeta is equal to n. In other words, what I'm saying is actually that this is actually these two probabilities are the same because these two events are the same. It's the same reason. Okay, so yeah, it's the same as this. Okay, for x in S bar n. Here it's because x is in S bar n. Okay, so now divide by probability that Wn is equal to -1 is equal to n, probability that zeta is equal to n. We get that the probability that the Vervat transform of xn is equal to x and I of xn is equal to k, conditionally given Wn is equal to -1, is 1 over n probability that xn is equal to x, conditionally given zeta equal n. And this indeed is a probability measure on S bar n. And this completes the proof. If you want, you sum over all x's, and you get that the probability that the I of xn is equal to k, conditionally given Wn is equal to -1, is 1 over n. So indeed, here you have a product. This shows you that the Vervat transform and the index are independent, conditionally given Wn -1, and identifies I of xn as a uniform distribution on 0, 1 up to n minus 1. Are there any questions on this? So if not, a teaser for the next episode. We will take mu of n such that sum from I, mu of I is less than 1. We will work with subcritical offspring distributions, and such that mu has a heavy tail. We will assume that mu behaves as n goes to infinity as some slowly varying function L to some power n to the power 1 plus beta. where beta will be taken strictly greater than 1 and L slowly varying. So what do I mean? That means that for every positive x fixed, L of for every positive u fixed, L of xu over L of x goes to 1 as x goes to infinity. For example, some examples of slowly varying functions. If you have a function L which converges to a positive constant as x goes to infinity, you have a slowly varying function. So actually, here I can write equal. Sorry. Another example of slowly varying function is log x for big X. Okay, and so we will, in the last lecture, we will take this offspring distribution, which is subcritical, which has a heavy tail. We will condition the random tree on having n vertices, and we'll see that a condensation phenomenon occurs, meaning that in this big random tree, we will have a unique vertex with macroscopic degree. The degree of this huge vertex will be of order n, constant times n, and all the other degrees will be very small. And we will try to understand, okay, what are the maximal degree of the other degrees? Okay, the maximal degree is of order n, but what are the maximum of the other degrees? Is it log n or n to some power or stuff like that? This vertex of macroscopic degree, what is its height with respect to the root? Is it equal to the root? Is it close to the root? Does it go to infinity? Okay, so these are questions we will answer in lecture 3. And to do so in lecture 2, we will study the random walks associated with this offspring distribution. And maybe just to finish, explain what will be the thing. And note that what is the expectation of the random walk, of one jump of the random walk associated to an offspring distribution? So it's the sum over L. How do I write it? If I write it, how is this okay? Yeah. Okay. I get some okay, so if we look at the random walk associated with this offspring distribution, it has a negative drift if the offspring distribution is subcritical. So the question is, okay, we have a random walk which has a negative drift. We condition it on going back to -1 for the first time at time n, or up to doing a Vervat transformation. You have your random walk which has a negative drift. We force it at time n to be back to -1. We do this and then we do the Vervat transformation. What will it do typically? So it has a negative drift, but at time n has to be back at -1. And this condition, this heavy tail condition, will impose a one big jump principle. So we will see tomorrow that there will be a unique big jump, a huge big jump. And when we do the Vervat transform, we get the Lukasiewicz path of the tree. So we have a huge jump which corresponds to this vertex with macroscopic degree. Okay, and then we'll try to understand, okay, where is this vertex located and so on. So this is just to give you a glimpse of what is coming. Okay, so that's all for today. Thank you.